we have already seen the previous technique, that is matrix associative memories. Now we shall have a look at the second technique or second procedure, that is second non-iterative procedure for association. So the second non-iterative procedure for association is called as least squares procedure. Now basically it is dependent upon, now this least square procedure is dependent upon what we have already seen, Wiederoth learning rule. So basically in matrix association memories we have used the Hebbian learning rule or the Hebb's law so as to define the weights, whereas in this particular case we will be using the criteria of minimizing the error, and that is given by Wiederoth. So in MAM the weight matrix which was defined by using the Hebb's law was given like this: summation of P is equal to, small p is equal to 1 to capital P dP into IP transpose. So in matrix form it was given as I transpose. This way it was represented. Okay, both these are matrices only, D and I. Now in LSP the weight matrix can be obtained by using a criteria which will be minimizing the error. So we will be using the criterion of minimizing the mean square error. Now in this case the weight matrix whichever we would be finding will be indicated as capital omega. So we shall check what will be this error, mean square error, which will be, I would be calling it as capital E, and how we are going to minimize this particular error, and what would be the weight matrix which would be helping us to minimize this mean square error. Now consider the input pattern IP. I am using a pattern IP which is used to simulate the network, and whenever we are given the input pattern, whenever we are presented the input pattern out IP, the output pattern generated will be omega times IP, because usually we write W into I or W into X. So here it is nothing but W is nothing but omega and input is nothing but IP. So this particular output pattern which is generated IP has to be as close as possible to the desired output pattern which is indicated as dP. So basically we need to find the error. So this error, whatever I am going to defining, it will be the mean square error. So the mean square error will be defined as E is nothing but, now basically I am presenting only one pattern at a time now, but while finding the error we need to take into consideration the error which is present every time a particular pattern is presented. So for that purpose I need to take summation of small p is equal to 1 to capital P, and then I take the norm of dP minus. So this is what I have taken. So what I said is that if at all this particular output, whatever we get, which I have indicated as omega times IP, it has to be close to dP. And if at all both are the same, then the error will be 0. But if at all it is not the same, and then there will be some error. Now this error has to be made minimum as possible. Now we already know how to make the error minimum, or how to find the minimum of this error. What do we do is that in order to find the minimum value of the error, we would be taking the derivative of the error with respect to the weight matrix, with respect to the weights. So now what we will be doing next is we will be taking the derivative of the error. So E is a quadratic function, as you can see, whose second derivative is positive. So we need to find the weights such that it will be minimizing the error. Okay, so that is what we would be doing, and based upon that we would be finding the values of omega. I can simplify this equation further. So I have split this. Now this dp will be made up of first, second, third, etc. So I am going to write this dp1 every time. Second time it will be dp2, and basically these two are, this will be a weight matrix and this will be a vector. So basically that also will be having the I will be having the first row corresponding to the first pattern and so on and so forth. So every time I am going to simplify this equation, and here it will be omega 2 comma j I pj and so on and so forth. So up till I will be getting here, the last term will be dp m. Okay, m is the last one, minus summation of j capital omega m comma j I p j the whole square, and then I close the bracket. Now based upon this I need to find the derivative. So what we do is that we differentiate the error. As I already told you, the quadratic function, E error is a quadratic function, second derivative is positive. The moment the second derivative is positive, I know that there will be a minimum which will exist. If at all the second derivative is negative, a maximum exists. But if at all the second derivative is positive, minimum exists. So in order to find the minimum, what we are going to do is that we are going to differentiate the error with respect to the weight omega j comma L, and we shall be solving this in order to find the weights. So when I differentiate, I will get dou E upon dou omega j comma L, and this whole thing which is in the brackets, okay, what will happen is that at every time, if at all I do this, I will get, so if we are differentiating for one particular neuron, that is the jth neuron, we are going to do it. So what we would be getting is that here we would be getting, since there is square out everywhere, this square will come out, so it will become as, and minus sign also will come out later, and within the bracket what we have is that we would be having summation of small p is equal to 1 to capital P. Now every time what you will get is you will be getting dp, so dp j I will be getting, because I am telling that I am doing it with respect to one particular, okay, I am doing it for one particular thing, that is dpj. So inside I will be getting dpj, I will be getting summation. Here I have to use a different variable here, summation of k is equal to 1 to n omega jk and I pk. So I would be getting this, and then this whatever is there, the same thing would be multiplied out as IPL. So we would be getting this equation. Now we need to simplify this particular equation. So what I will be doing is that this I am equating to 0, because that is what is the procedure to find the minimum. So then what I do is that I am taking summation of, so now this I can write it as dpjipl, and then I will be getting one more summation which will be coming, minus summation of p is equal to 1 to capital P. Okay, this 2 I can just ignore because it is equated to 0, right? So this 2 will have no meaning here. So this is what we will get. Now what we can do here is that Since if at all you see here, this omega jk is not dependent upon p, only these two are dependent upon p, so I can still simplify it. And I can take this summation out, omega j comma k, and here I would be getting small p is equal to 1 to capital P, IPK and IPL, and this I can write is equal to 0. So when it is equal to 0, I can take it on the other side, and if at all you see, what happens is that this is nothing but summation of P is equal to 1 to capital P dP and IP transpose. This is the same thing whatever we had written previously. This, okay, let me first take it on the other side, then I will show it to you. So now, please note this whatever we have here, I can write it in the form of the vectors. I can write it in the form of vectors. This is dP. Now please note this is, when I write dP, it is made up of dP1, dP2, dP3, etc. So now I am going to write this entire vector, and this is also vector which is IP transpose. So this is P is equal to 1 to capital P. And this will become the matrix, and this will become another vector. This is also going to be, I am going to write in the form of the vectors. Okay. So now we need to find the value of omega. So how we need to find the value of omega? I take omega, and in order to find omega values, will be P is equal to 1 to P, dP, IP, and denominator it would be nothing but small p is equal to 1 to capital P, IP and IP transpose. So now if all you see this is in the denominator. Denominator means I can get it in the numerator. So by taking the inverse. So I take the inverse, and I would be getting this, and once I get this, I can write the equation in the form of matrices. So how I do that? This part is nothing but D into I transpose. So I have D into I transpose. And what is this? This is nothing but, okay, I forgot to write the inverse here. This is I into I transpose, and then I have to take the inverse of it. So basically what I get is that I get I into I transpose and the inverse of it. So this is the equation which is used to find the weights. Okay? This is the equation which is used to find the weights. So basically, and if at all we observe, this least square method normalizes the Hebbian weight matrix. What is Hebbian weight matrix? This part is the Hebbian weight matrix. Okay, so it is trying to normalize the Hebbian weight matrix using the inverse of I into I transpose. Now this particular technique will not be, okay, we will not be used for auto association tasks. Why? Why it will not be useful for auto association tasks? We shall see. So for auto association tasks, what happens is that this technique cannot be used. Now, in case of auto association, there will be no D. D will be same as I. Okay. So what will be the weight? Omega will be nothing but I transpose into I transpose inverse. So what is this? A into A inverse. Okay. A matrix into the inverse of the matrix. And this is nothing but identity matrix. Okay. This is nothing but identity matrix. Now please note. So basically it would be trivially associating the vector to itself, auto associating vector to itself. So you know this particular thing cannot be used. Now please note, whenever I am using the symbol I, the symbol I here is like this, cursive. Okay, because identity matrix is this way, I. So whenever I am using the I here, I am making it a point to have a cursive I which should look like a J. Okay, so you need to take care of that. Now second thing is that there might be a problem. Okay, second thing is that there might be a problem wherein the inverse doesn't exist. Okay, so at times there will be, so there may be a problem when I into I transpose doesn't have an inverse. Okay, so it doesn't have an inverse, so there it will be a problem. So in that case, what has to be done is that you will have to use another technique which uses a pseudo inverse. So it has to use a pseudo inverse. Now when inverse doesn't exist, when you know that the determinant, how you will come to know that the inverse doesn't exist? The determinant of I into I transpose will be equal to 0. So if this happens, then you know the inverse will not exist. So in this case, you may have to use a pseudo inverse. So this is what happens in the next technique, that is OLAM, optimal linear associative memory. So before we go to that, we shall solve a problem on this particular technique of LSP, least square procedure. So this would be the equation for the weight update which has to be used.